All right, we are preparing to stream the meeting. Just 1 second. Okay, we're live. Welcome everyone to a new installment of our Quantum Matter seminars. We know that many of you have started teaching or are attending lectures. You know, the semester has started in many places. But as long as this situation goes on and there is no end in sight so far, we're going to continue with our seminars throughout the rest of the year and in the same time slot. And so if you're not able to attend live, you can still stream the recorded version on YouTube. So after this announcement, okay, it's time to introduce our speaker today. It's a pleasure to have Marcos Rigol from Penn State. Thank you, Marcos, for being here with us today. Please go ahead.
Okay, thanks, Adrian, for inviting me. So it's a pleasure to join you guys. So, okay, so today I'm going to be telling you about many-body quantum systems far from equilibrium. And I have a very particular way of taking these systems out of equilibrium, which people call technically geometric quenches, which is, you can think of it as you have a box and you open the box. So you don't change interaction or anything, you change something about the geometry of the system. And now what I'm going to show you is that when you do that, something very interesting can happen. So I'm going to show you that the system, you think of it as being very far from equilibrium, but it turns out that it could be an eigenstate or could be even the ground state of some emergent Hamiltonian. So that's essentially, in a few sentences, what I'm going to be telling you today. So this is work that I have done in collaboration with 3 former postdocs, a former graduate student, current graduate student. So I'm going to be also showing you results from experiments. So these are experiments done in the group of Dave Weiss at Penn State. And really early on, I started thinking about these problems when I was a graduate student. So Alejandro was my PhD supervisor. And so you will see there will be some works with him that I also want to mention. Okay, so this is the plan. So the first thing I want to do is I want to show you experiments. I want to make sure that you see that these things I'm going to be talking about are seen experimentally. So, and that's going to be very fast. And one of the experiments was done at Penn State. The other one was done in the group of Immanuel Bloch in Munich. Then I'm going to be telling you the background to those experiments, which were those works that I actually did during my PhD in the early 2000s. And then the rest of the talk is really the new results. And that's this idea of those states being eigenstate of some emerging Hamiltonian. So the first part of the talk is going to be about pure states. And I want to generalize that to thermal equilibrium states. Now, these 2 parts is all about systems that can be mapped onto non-interacting systems. You will see what that means. And then towards the end is more technical. I'm going to be talking about fully interacting systems. So you see, every time I stop one of these parts, it's kind of a natural point if you have questions to stop me. Okay, so and then I will summarize at the end. So let's start with the experiments. So the first thing I want you to keep in mind is I'm going to be talking about one-dimensional systems. So on the way they are created in experiments, usually is using 2-dimensional optical lattices. And this is the way you get an array of one-dimensional systems. These gases are very cold. So essentially the interaction between atoms, and I will have in mind bosonic atoms, is a contact interaction in 1D. And the great thing is that in the experiments, they can change that contact interaction by changing the 3-dimensional scattering length that is done on this AS. And they can also change them by changing the confinement in the transverse direction here, which is as easy for them as increasing the power of their lasers. Okay, so changing these 2 things, you can change this G1D. Now, when you think about bosons in 1 dimension with contact interactions, so It's something that is not new. Actually, it's a model introduced by Lieb and Liniger in '63. And it's very special. It's what is called an integrable model. So we can really obtain exact analytic expressions for the thermodynamics, correlation functions, and so on. And then in the experiments, you see they can make this term very close to 1. So, and you will see that means that this G can be very large. So in that limit, you can think of these bosons as being infinitely repulsive in real space. So it's like fermions. They don't want to be on the same place. And that's even another model that was introduced earlier by Girardot, and is now known under the Thom-Girardot regime, in which now the bosons behave like fermions. So the first experiments in which this was explored were done in the group of Dave Weiss at Penn State. So there are 2 papers. So these are somehow probably the results that bring the idea home. So what is shown here is the experimental measurement of what is called as this local G2. You see what it is. It tells you about the overlap between bosons, properly normalized. And it's plot in here, so this is G2, is plot as a function of this gamma effective. Is what parameterizes interaction in this Lieb-Liniger model. And you see it has this G1D, which I show you here. And then in the bottom, it has the density. So essentially, if you decrease the density in 1D, you get these to be larger. So they become more strongly correlated. It's similar to the effect of increasing G. And now the points in here are experiments, and they are different sets of runs in which they change this omega perp and they change this n. And the line is essentially the Lieb-Liniger prediction. And you see that it really matches very well the experimental measurements. So the other thing that you can do in these experiments is add another lattice in this direction, right? So that now these bosons are not in continuous space, they start hopping, and condensed matter we like lattice models. So this was done in experiments in the group of Immanuel Bloch. And now you have very strongly interacting bosons. So you see in the lattice, you should think about now the particles they have on-site repulsions and they can hop around. So in the limit in which this is very large, you can map, and I'm going to show you, you can map this model into a spin model that is exactly solvable. And these are experimental results. The point are experimental results for momentum distribution function that they measure with time of flight. We are going to be showing a lot of these things today. And the line is the theory just using these ideas of the mapping. And the important thing to keep in mind, this is momentum. So in the instead you have the density distribution, is that these experiments were done in the regime in which the occupation of the site is smaller than 1, okay? It's less than 1 particle per site. So, okay, that's great. That tells that they have a good experimental handle in controlling things and really comparing to exact solutions. That's probably not the most interesting thing actually for us because we know a lot about equilibrium. So probably the most interesting thing is what happens when you take those systems out of equilibrium. And this is what I'm going to be showing you next, what happens. So the first experiment I'm going to be showing you is in the same group from Immanuel Bloch. And now what I'm going to show you is what happens if you take these gases that are infinitely repulsive, if you want, in the Thom-Girardot regime or hardcore bosons. And you fill lattice sites so that you have a density 1. That's what we know as a Moore insulator. And you let them expand. Okay, so now let me show you the experimental results. So this is what happens as a function of time with the density in these 1D tubes. So now remember, so I told you there are a bunch of them. So even if you have density 1 in some of them, so the extent of this Moore insulator is different. That's why you never see a plateauing here in this density. So this is an average over tubes. And well, they expand, nothing very exciting. So there is the experiment is in black. There is some theoretical treatment that I will show you how this is done in a minute. So, but then there is some theory to it. Not very exciting. So really the exciting thing, and was what we found like many years ago, is what happens in momentum space. Okay, so you have a Moore insulator. This system has very short correlation. So since they do time of flight, what they get is an image like this, where there are several Brillouin zones. So if you want to think about it in your lattice model and you want to forget about the continuous, so you can focus on this part in here. And the fact that you have this a very small peak, it just tells you that you have some sort of very short correlation length. Okay, so that's something that was known. So, and now you let it expand, and this is very important. This is not a time of flight. So you let it expand in one dimension in the presence of the lattice, so that these bosons are interacting as they expand. You see that things start to change, right? And peaks start to merge. And here you see that at the longest time, now you have peaks that are sharper than the one you had originally. Actually, in the theory, they are even sharper. So, and what that's showing is that when you let that system expand, essentially correlations develop between the atoms, and you will see that it leads to emergence of quasi-condensation. Okay, so that's the first experiment. So you see, you start with something that is uncorrelated. It's a Moore insulator. You let it expand, you get something that has quasi-long range correlations. So now let me show you a completely different experiment. Okay, so maybe it's the contrast, but it's going to be surprising maybe. So now let's think about starting, instead of with a Moore insulator, let's start with a system that has correlation. So one of these superfluids at very low temperatures, and now no lattice. Okay, that's the kind of things that are done in the experiment of David Weiss. So you see, this is again momentum distribution function. It's plotted here as in terms of position because they take pictures, but you can think of this as momentum. So at 0 time, you see it's very different from that experiment of Immanuel Bloch. You have some peak, okay? So originally in the other experiment at time 0, there was almost no peak. So, and now you again let these bosons expand in one dimension. And what happens is the opposite of what happened before, right? Before you had no peak and a peak emerged. So in here you have a peak and the peak disappears. Okay, what's different here is there is no lattice, okay? And the initial state is not a Moore insulator. So this is a problem that we've looked at in great detail theoretically. So we can really calculate exactly what the momentum distribution function should be, okay? Remember, this is a time of flight measurement, and this is what it should look like. So, and you see at long times, this is very similar. But as you get to shorter times, it's different, right? So essentially, in the momentum distribution function, we have these sharp peaks I'm going to be discussing also later. And they are different from the experiments. And this is actually due to an experimental imperfection, is that they have to wait for some time that things expand, and they only have some, the cameras have a finite size, so they cannot wait arbitrarily long time. So there are effects of finite time of flight. So we've calculated those effects, again, exactly because we know all correlations in this state. And if we do that, this is what we get. Okay, so now this is experiment and this is theory. Okay? So now you can see, actually, let me just show you comparing one by one. So this is a comparison in here between this and this. So you see the theory has slightly more coherence. But as you go to non-zero times, then you see you don't see the difference. Okay, so this is the degree of, and there are no free parameters in this comparison. So now, why is this remarkable? Apart from the fact that it's completely the opposite of what I was showing you before, is that now what I'm going to do is at the longest time, I'm going to show you the experimental measurement, the momentum distribution function of the bosons, this corrected by time of flight. So there are 3, but if you look at this, there are 4 curves in here. So the fourth curve in this plot is the momentum distribution function of non-interacting fermions in exactly the same track. So, and the remarkable thing in here is that if you take a picture, and what they did, and you don't tell the experimentalists, or whether they don't know, so you show them a picture, and they will not think that these are bosons. They actually would think that these are fermions in equilibrium. Okay, so this is more or less the the phenomenology that I want to discuss with you today. So, and at this point, I can take if there are some urgent questions about the experiment, I can take questions before I go into a bit more detail of what is happening in these two experiments.
Okay, so if you want to ask a question, just raise your hand or put something in the chat. Okay, I think we're good.
Okay, good. So now then let's see. Let's give you some more time to think about these experiments and then ask questions. So how are we going to be thinking about this system? So for simplicity, even the continued case, we can always think of it as a system in a lattice at very low fields. So I'm going to think about them as hardcore bosons. So these are bosons that have an on-site repulsion which is much larger than the Hopin. So if that happens, you see at low energies, you can think of a model in which you have the bosons moving around. They are in a potential, and this strong interaction is just replaced by a constraint. So you cannot have more than one boson per site. Okay, so and then if that happens, then you can map those hardcore bosons into spins. And then the spins into fermions by something that is called the Jordan-Wigner transformation. That is a non-local transformation. And then you go from this Hamiltonian that you cannot diagonalize because of this constraint to one with free fermions that you can diagonalize. And for free, you immediately get something that in this system will always be conserved, even though it's not easy to see in terms of the bosons. What is always going to be conserved is, since the fermions are not interacting, are the occupation of the single particle states of the fermions. Okay, so these are conserved quantities, and you can think of these fermions now as the underlying quasi-particles for these hardcore bosons, so free quasi-particles. Okay, so these occupations are going to be conserved. And now that immediately tells you that this momentum distribution function of the bosons that I was showing you, that is equal to the ones of the fermions, well, this thing is behind that. You could map the bosons to the fermions, and those momentum distribution function of the fermions are essentially conserved. So the big problem really when it comes from going from the bosons to the fermions is not in the thermodynamics. Essentially, you have the Hamiltonian is the same, is in the correlation functions. So for example, if you want to compute momentum distribution functions, right, you have to compute one-body correlations for the bosons. When you write it in terms of the fermions, then you have all these non-local strings. Okay, so that complicates things. And on top of that, if you want to look at dynamics, so this state will not be the ground state or an eigenstate. It will be a time-evolving state where here you have this free fermionic Hamiltonian. So the way we go about doing that is using properties of Slater determinants. Is like you can prove that exponentials that are bilinear in creation annihilation operators of fermions acting on Slater determinants, they give you a new Slater determinant. We know how that works. And you see, this is also bilinear. We know how to create a fermion Slater determinant. So in the end, these you can show that you can calculate these correlations in terms of determinants of products of matrices. So, and this can be done very efficiently, and that's why we can do very large system sizes. So it's just to let you know that everything, all the results I'm going to be showing you are essentially exact in this sense. Okay, good. So this is what's behind these calculations I'm going to show you that I did many years ago. So what happens in the ground state? So let's take a look at this, because that's what makes the difference between this fermionization and this emergence of the coherence. So if you are at low fillings in the lattice, and I emphasize that was the regime of the earlier experiments of Immanuel Bloch, these bosons, they like to condense, but they cannot because it's one dimension, so they quasi-condense. So that's why the momentum distribution function is this charping. Okay. So now, if you put too many bosons there, you cannot have more than one per site, right? We talk about this constraint. So this is this more insulator I was telling you that Immanuel Bloch used as an initial state for that expansion. So you see, if you make it just a pure more insulator in this hardcore picture, you would have occupation. You could have things are localized in space, completely localized in momentum. So they are localized in position, they localize in momentum. So the reason you have these little peaks is because of these regions in here. Okay. So now let me study the dynamics of pure Moore insulators, and let's see what happens. So, okay, so what I'm going to show you now is the exact calculation of what happens when you take these bosons and let them expand in one dimension. So this is the exact dynamics. So, and what you see is exactly what they saw in the experiments at long time. So as the bosons expand, you get that peaks emerge, okay, in momentum space. But notice that they don't emerge at zero momentum as in the ground state. They emerge at finite momentum. So this is exactly what was seen in the experiments. Now, in theory, we can do more, right? Because we have all the knowledge about the correlations and so on. So we can, for example, take this one body correlation matrix and diagonalize it, look at the largest eigenvalue and the associated wave function. They are called natural orbitals. So what I'm going to show you now is an animation of what this highest occupied orbital looks like. And these are the occupation of all orbitals. So you see, initially, they are all one. Okay, the orbitals are just all localized. Now let's see what happens when I let this guy expand. Now you see that something is forming around the Moore insulator, which is melting, and once it's melted, it's just expanding out. Okay, and that's that picture of these quasi-condensates that are being formed, and once created, they move out like solitons. And you see they have many particles in them, right? So over 10 for this system with the order of 100. Okay, so now this is something that one can essentially not look at experimentally, but we know that this is what is happening behind. Okay, so now the question is, of course, you could say, well, but are these guys that are emerging here the same that are in these peaks in here? And since they are solitons, what we can do is we can measure their position, okay, and plot it as a function of time. And it's a line. So, okay, there is a velocity. So, or there is a speed here that we can calculate. And given that we know the dispersion relation in the lattice, we can find what is the k that corresponds to those bosons. And surely enough is this k at which you see the peaks. Okay, so that's very nice. It's like a classical calculation. You can see it. Now, more interesting, you can look at the occupation of those peaks or the occupation of those natural orbitals and scale with the square root of the number of particles. And what is amazing about it is that that's exactly what happens in the ground state. So that's why those peaks that you saw at finite momentum look so similar to the ones I showed you before for the ground state. And if you look at the one body correlations, they decay as 1 over the square root of the distance between the points. And that's exactly what happens in the ground state. Okay, so that already tells you that there is something very, very interesting happening. So you have this system that is very far from equilibrium, is expanding, and the correlation look like in a ground state. So now let's change and see what happens in the other case, in which you start at low fillings. Okay, and this dynamical fermionization. So you see now the filling, you see here the occupation is much smaller than 1. This is the peak that you get in the ground state at 0 temperature. And this is the momentum distribution function of the fermions that underline this system. So this is what I was telling you, that distribution is conserved, okay, for the bosons as they expand. This is a conserved quantity. And now we can see what the dynamics does. And surely enough, you see that as the bosons expand in real space, their momentum distribution function matches the one of the fermions. And that's what was seen experimentally. Now, you may think, well, does that mean that then you cannot tell apart these bosons from fermions? And actually you can. And this is what is most surprising. So even though I'm showing you the momentum distribution function looks like the fermions, if I look at the one body correlations, right, which I showed you before for the other case, you see, I show you this power law here that I told you that is 1 over square root of x. So if I do the same for these fermionized bosons, the one body correlations decay exactly with the same power law. Okay, so how come that they have the same power law, but you cannot see it in momentum is because their phases are scrambled. So you see the colors correspond to the same colors here. And even after very short times, you see, in which you cannot see the difference in here, you already get the faces scramble. And that's why when you do the integral to go to momentum, you cannot see the peak. Okay, so that's the puzzle, right? How come that these two systems that are very far from equilibrium, they are expanding, they exhibit correlations which are exactly the same that the system would have in the ground state. Okay, so that's the big question that I want to address. So at this point, I can again take questions if you have any before I try to tell you what's behind all this.
Okay, I don't see anything in the chat. So
okay, perfect. Okay, so then let's continue. So essentially now you saw the experiments, you see what's happening, and now what I'm going to try to explain is why this is happening. So in this, really this melting of the Moore insulator, which people also talk about it as the domain wall melting in the context of spins, was very helpful. So that was what sent us on the right track. So we studied that in the context of hardcore bosons. I show you the result, but there were earlier results for fermions, and they also had seen these ground state correlations emerge. So and that gave us the idea that maybe one can use ground states to describe this system. So we wrote a few papers, and Adrian was involved in one of them, building like in ground state in homogeneous field, which would exactly describe what happens in this system far from equilibrium. But and it was also used later to even compute entanglement entropies. It turns out that the entanglement entropy of those states are exactly the same as ground state entanglement entropies in homogeneous fields. So but at that point we had not asked really the crucial question, so which we asked much later, and that's why it's important that you know, younger guys take a look at things, because they come with new ideas. And the question is this: could it be that these time evolving states are actually ground states? I mean, that's a you know, pretty big leap to think of. And the answer is yes. So once you ask that question, you will see how that works out. Okay. So we look at models that are mappable to free fermions and to the spin 1/2 excitation. So let's try to put this into some mathematical framework. So how do we think of this? So what we are doing here is a quench, and as I mentioned before, it's a geometric quench. So you can think of it like we have a system that is trapped and we turn off the trap. Okay, so the initial state is an eigenstate of some local Hamiltonian, and then it evolves under a new local Hamiltonian. So H0 and H are local, and that's important. So okay, so let's go through the math. So the initial state is an eigenstate. The time evolving state is e to the minus I H. This is a new Hamiltonian. Okay, these two Hamiltonians are different and they don't commute, or else nothing would happen. Okay, so and now you can just take this equation here, multiply by e to the minus IHT on the left, and you can see that you can rewrite it this way. Okay, I just completed here with this an identity, and e to the minus IHT went through this scalar here. So this is interesting. This time evolving state is an eigenstate of an operator that we know, right? But this is in general useless. And the reason this is useless is that this operator is very non-local, right? Because you see, you have, when you expand e to the IHT, you get all these commutators. And every time you get a commutator, you increase the support of the operators. Okay, so this is local. Then this one, if this one has two sides, this will have three sides, and so on and so forth. So it's not very useful. But you can see that if for some reason this commutator gives you something that is conserved, then this expansion is truncated. And exactly, right? It's not a short time or anything. It's just that the rest of the terms are zero. And now you will have that your time evolving state is an eigenstate, okay, of a new operator. And whenever this happens, that is truncated, we redefine this M as an H because we want to think about it as a local emergent Hamiltonian. Okay, M in general is non-local, H is local. Okay, and that would be essentially the idea for why this could happen. So essentially, in the Heisenberg picture, this Hamiltonian is just this constant in here, right? And so this H of t is a local conserved one. Okay, very simple idea. So how does that work in practice? Okay, so let's take a look at first this domain wall melting. So the domain wall is an eigenstate of this operator, right? And you see, I'm thinking about really half of that Moore insulator, right? So you remember the Moore insulator expanded in both directions. So I'm really putting a wall and then taking a domain wall and letting it expand. So this is the ground state of this operator. Everyone can see that this L is 1, 2, 3, 4, 5. So you start putting particles where the potential is the smallest. Okay, and this is the physical Hamiltonian, right? So your state is an eigenstate of this, and it evolved from this Hamiltonian. Well, but it turns out that this operator is what is known as the boost operator for this Hamiltonian. When you commute the two, what you get is the particle current. Okay, so the commutator of this with this gives you the current operator. And that one is conserved up to boundary terms. Remember that I told you I had a wall. So that would be it. So essentially what I'm saying is that that state in which you see the peaks emerging is essentially the ground state of this Hamiltonian. Okay. Now here one, if you think about it, is I mean the story cannot be that simple, and it comes from all the details up to boundary terms. So you see the initial state I was telling you, right, is a domain wall. There is no current in that state, right? Now as time goes, you immediately realize that there is a current because particles are moving in one direction. And the reason that current is there is because the current is not exactly conserved. So you see the commutator of these two extensive operators is something that lives at the boundary. Okay, so and that's what makes the difference, and that in the end is what makes these emergent eigenstate solutions something that can only work for some time and not for arbitrarily long times. Okay, so then essentially now once you know that, you want to go back and say, well, then what is the correction because of this? So you go to the Heisenberg picture and try to commute all these commutators, compute them all. So the first one I already told you what it is this. Now in a state in which it has a domain wall, you see this N1 is 1 and NL at the end of the chain is empty, so it's 0. So you see that this, the expectation value of this is just a number that depends on time. So you can absorb that in the lambda I had before. The eigenvalue is a renormalization of that. So it's not very important. Now, what is remarkable is that if you start computing the next terms, they all vanish. And to really determine up to where they vanish, you have to decide how many particles you want to put in your domain wall. So if you want to have a domain wall that is half the size, so the occupied part is half of the lattice. So this is what I did here. N is the number of particles, is half of the entire system size. So you get that all higher order terms vanish up to one that looks like this. Okay, so this is the first number. You see that the how high it is in the commutator comes from this power of t. Okay, and these ends are large, so you can use Stirling approximation and see when is it that this is exponentially small. And you see here you have t to the 2n, and here you have the beautiful factorial that makes everything small. So if you use Stirling approximation, you see that these terms are exponentially small so long as t smaller than 2 times n over e. Now, if you think a bit more about this, you realize, well, these particles are spreading ballistically. So this is equivalent to saying that this is going to be valid so long as the first particle, right, in your domain wall doesn't hit the right boundary. Or you could think about it that the holes don't hit the left boundary. Okay, so it's not like this emergent eigenstate solution is going to work forever. It's just going to work up to that time. And if your system is infinite, it will just work forever. So now we can go and test that numerically. So we can take the Hamiltonian and do the exact calculation for the time evolution. We can take the emergent Hamiltonian and do the exact calculation for the ground state and compute the overlap. And this is T over N. And you see that up to 0.5, these are different system sizes, okay, in which the change size is twice the number of particles. You see is 1 precisely up to 1/2. So, and now if you want to see how close to 1 it is, it's actually machine precision. So you can plot 1 minus the overlap, and you see that is essentially machine precision up to 1/2, and as you increase system size, this becomes sharper. So that tells you that it really works up to that point. Okay, and that's ultimately the solution of what was happening. So we see these correlations being ground state because the state is a ground state of that emergent Hamiltonian, which is modified by that current operator. So it's not a hopping what it has in there, it's a current operator. Okay, so now how does it work for the other case, the case in which you have the trap and no lattice? As I said, you can think of it as a system in a lattice at very low filling. So now we have to see that the initial state is a ground state of a Hamiltonian that looks like this. And we write it with alpha because we can think of this for arbitrary powers, but for the harmonic trap, alpha will be 2. Okay, so this is the initial state is a ground state of this Hamiltonian. The physical Hamiltonian is this guy. When you commute these two for alpha equal to, the first term is not something that is conserved. But it turns out that when you compute the next commutator, then it's something that is conserved. So in that case, the emergent Hamiltonian is more complicated than the one I showed you before. It has a linear in T term and a quadratic in T term. Okay, and these operators here are, this is a generalized current operator, which I just defined here. This is a generalized kinetic energy operator, and this is a total number of particles. So, and that's what happens essentially now. So if you, instead of having a boost operator, which is this linear potential, you have quadratic, quartic trap, what happens is that the initial commutators don't produce conserved quantities, but later commutators do. Okay, so now what we can do is just take that Hamiltonian, compute the ground state at very long times. So for example, at T0, this would be this ground state I showed you before. At T very long, 1000, we compute the ground state and compute the momentum distribution in that ground state. And you see it matches the fermionic distribution. So in the occupations at that time, you saw it here. So this is the initial occupation. And then at very long times in real space, it looks like this. So we've done it too for the quartic potential. I'm not going to show you the expression for the emergent Hamiltonian. It's very long, but it works the same. Okay, so that's ultimately then what's behind these universal correlations that are ground state in these systems far from equilibrium. So, and that's another point at which I can take questions if there is any.
Okay, you can raise your hands if you have any questions. I don't see anything in the chat, so okay. I guess. Oh, okay. Yeah, so we have someone asking what happens if the trap is not harmonic, but I think your last slide demonstrates what happens.
Right, if it's quartic, we can calculate other powers and it will work. It's just much more complicated. The emergent Hamiltonian would be much more complicated.
Okay.
Good. So then, of course, you would ask, like, you could think of, well, that's beautiful, but you know, real systems, they are not in pure state, not ground state. So in the experiments, they are at some finite temperature. You have mixed states. I mean, what happens? So then let's look at what happens at finite temperature, right? Now, calculations at finite temperature. So if you want to compute one-body correlations, you have to evaluate this expression, right? When you map it to fermions, it looks a bit complicated. I'm not going to get into the details. So Many years ago, I looked at this in equilibrium, and we recently generalized to dynamics. It can be done exactly, just believe me, it's something that you have to compute determinants and the subtraction of determinants, and it's something that you can do very efficiently. It's not a many-body calculation. Again, I mean, many-body in the sense of Hilbert space involving Hilbert spaces. It involves powers of the system size. So we can do that also exactly. So let's take a look at then at what happens if we take that domain wall at finite temperature. So we take the finite temperature state for this Hamiltonian and let it expand at different temperatures, okay? 0.1 in units of this J and KV1, okay? So what is shown here is this is time, this is momentum, and then the momentum distribution function is coded in the colors. And this sharp thing, this line here shows you that, again, you get this peak that emerges at before 0.5, but then move toward 0.5. And the higher the temperature, the smaller the contrast. Okay? So not very surprising. So, but you have it, okay? It's not gone as soon as you put some finite temperature. So as a matter of fact, what you can look is at what is the occupation, how high that peak is for a given temperature as a function of the number of parts. And you see, well, for 0 temperature, it should be the square root of n that I showed you before. But if you start at finite temperature, you see it's still growing quickly, right? So you may wonder, well, is that what would happen if you have a ground state at finite temperature, or I'm sorry, a finite temperature state in equilibrium and increase the system size? And it is not. So if I take a box at a given temperature and half filling, and I increase the size, since correlations decay exponentially, you see that saturates much more quickly. So somehow this when we look at this, it suggested that the system may be somehow cooling effectively as it expands. And that's what I'm going to discuss next. Okay, so how do we think about now finite temperature? Well, the initial state now is a thermal state of your Hamiltonian, H0, with some inverse temperature beta. And the time evolving state is this state in here, which we can always write like this, right? So I just put the exponentials inside here. And this is great because you see now this you can redefine again as a very non-local operator, very similar to the one that I had before, which is in here, right? And essentially it tells you that the time evolution of this thermal state is a thermal state of some, in general, very non-local operator. But if that non-local operator, right, because of the expansion being truncated becomes local, then again, we can define this emergent Hamiltonian, and now you will say that your time evolving state is a thermal state of that emergent Hamiltonian. Okay, in the same way that the 0 temperature state was the ground state of that emergent Hamiltonian. Now in here, what is important is to notice that when you do that, you follow those equations, the beta that you get in here is the same that you had originally. Okay, so the temperature is the same. So which you immediately can say, well, then how could it possibly be cooling effectively? So let's take a look into that. So this is the initial Hamiltonian, the one that I have a finite temperature state. This is the physical one. And again, if you compute the emergent Hamiltonian, it looks like this. Okay, it's simpler actually than the harmonic trap because the t-squared terms are only boundary terms. But you can take this and rewrite it this way. Okay. And now let's take a look at this because it really has all the information now. What do we get in here? So we have this term which has, has an amplitude which is growing in time. We have this term in here which has a phase that depends on time, and you see the arctangent of something that is growing in time. So it means that these 5's like going towards this pi over 2, which is what you see the peak is doing, is going toward pi over 2. So then what is the cooling? Well, the cooling is just the fact that even though the beta is not changing, this amplitude is changing. So the energy scale associated with this term is growing. So the way you should think about it is really set the energy scale to 1, and then you see what's happening. So what's happening is now you have an effective Hamiltonian with this energy order 1, this term order 1, a trap that is decreasing its strength in time, and a temperature which is decreasing in time. Okay, and then I can show you now the results. So this is in real space and this is in momentum space. And again, here the color lines are the thermal state of those emergent Hamiltonians, and the black lines is the exact solution. So, and you see they agree. You see the peak moving in time, it's growing, and moving its position towards pi over 2. And if you look at the correlations, then is where you can most clearly see that it's effectively cooling. So these are the initial correlations are very short range, and then the correlation length is increasing in time. So that's to say that everything that I told you about ground states essentially is stable to finite temperature. So temperatures do not destroy it. And as a matter of fact, finite temperatures, what happens is you expand and you effectively cool. So probably that's why in the experiments, even if they didn't start with something that was very close to the ground state, they would still see these peaks. Okay, good. So with that, I have covered ground state and finite temperature, but these are systems that can be mapped onto non-interacting ones, right? So you could say, well, this is all physics of non-interacting particles, really, that are behind, or quasi-particles. So the final part is about fully interacting particles. So I can take questions if there are any about these models that are mappable to non-interacting models.
We might want to wait just a little bit because I think sometimes the questions are delayed in the chat. Well, okay, I'll let you know.
Okay, so then anyway, see, so if there are no urgent questions there, let me just show you the full interacting case, and then this one definitely just gets more technical, so I'm going to go very fast over it. So okay, so the model I'm going to be thinking is are now these fermions, which you saw before, with nearest neighbor interactions. And that's a model that in the spin language is known as the spin 1/2 XXX chain. So okay, so this is the Hamiltonian. So, and let's think about the domain world. So this is the Hamiltonian that will drive the dynamics. So you see, you can build a domain world that is an eigenstate, actually a very highly excited eigenstate of what is known as the boost operator for this Hamiltonian. So something that commuting with this Hamiltonian gives conserved currents. So and that's it. Then the entire procedure follows. So I start with an eigenstate of this operator, okay, do the dynamic with this operator, the commutator of these two give like a complicated operator that is known as the energy current. And then my emergent Hamiltonian is nothing but this guy plus this guy. Okay. So now showing that this works is more complicated because these interacting integrable models, even though they are integrable when you want to compute correlation functions and the like, is very complicated. So what I'm going to do is show you essentially exact normalization results. So I take the Hamiltonian, the initial state, and I compute the exact time evolving state. And I take the emergent Hamiltonian and I compute the exact eigenstate. I look at the overlaps and I show you the results. So this V non-zero is the interacting model. And I have also the non-interacting result just as reference so that you see, because actually they don't change that much for these overlaps. So these are chains with 6, 7, and 8 spinless fermions. So it's up to 16 sites. And you see the overlaps again being 1 up to 1/2, and then departing from there. So if you do 1 minus the overlap, it's similar. Of course, we can only look at small system sizes, which overlap with the free fermions. But if we do the free fermions for longer time, you see this moving towards 1/2, which is what I showed you before. So and that's nice. So essentially it tells you that if you can solve for this Hamiltonian, okay, then you don't need to do quantum dynamics. So you can just look at correlation functions. You can look at the site occupations, momentum distribution, density correlations, what have you. And then you will have the result of the exact dynamics. So in this particular case, you can see the occupations at different times. for that V 1.2 for 8 particles. And now you can look at the momentum distribution function. You see the peak is not at pi/2 because of those interactions. So it's smooth. And so there are many things that change, but the picture remains the same. So essentially, that time evolving state of this interacting model is an eigenstate of an emergent Hamiltonian. Okay, so with that, I'm going to stop. And let me just summarize what I've been telling you. So I've been showing you that in these geometric quenches involving integrable systems, and those geometric quenches, what they do is they result in transport far from equilibrium. So this is not linear response, right? This is not something in which you are looking at small changes in the density. We are looking at changes that go as large as they can be, from like 0 to 1. So, well, those geometric quenches can produce states that are eigenstate of emergent Hamiltonians, and we know how to compute those Hamiltonians. If you have finite temperature states, then they produce Gibbs states of the emergent Hamiltonians, and it works for interacting or non-interacting models. So the final thing that is really interesting is that even though we were dealing with integrable models, I only use one conserved quantity, so, or quasi-conserved, right? It was conserved up to the boundary effect. So which, raises the question of whether one could use these for non-integrable systems. So we have explored these ideas in other contexts. So for example, to devise adiabatic protocols to transfer inhomogeneous state or trap states into like, for example, box traps, and also for SUN fermions and so on. But so you can look at these papers if that rings a bell. So with that, let me just thank my collaborators, especially Leo Widmer, who has been the main driving force for these new results and the support of these agencies. And thank you for your attention.
All right, thank you very much. It was a very, very interesting talk. So I think we have one question in the chat, and I'm going to read it here. So this question says, can this be generalized to the Calogero-Sutherland model? I'm not sure what that is, but
right, it's a specific model with. So I don't know. I haven't thought. I haven't given it a thought.
Okay. I guess maybe in a question I had is that, so this seems all very generic. Have you, I mean, it's very difficult to do this in higher dimensions, but do you believe that this would also work in higher dimensions as well?
I mean, it's that's this big question in here, right? Yeah. Only one conserved quantity. So really the only models for which we found that structure, right, in which you have a local operator, right? You commute it with another local operator, or you have a local operator commuted with another one, give you a current, something that is conserved. I mean, we only know that for integrable models. Yeah. And once you have integrable, you think, okay, it has to be integrable. Then if it is interacting, it will only be in one dimension.
Right.
Okay. So but if you are okay with not interacting, then this would apply to any dimension because the currents are conserved there. So the question is for interacting models, we only know how that works in one dimension.
Okay. Yeah, makes sense. All right. So any other questions? Raise your hand and you can talk to Marcus via chat, or we can also submit a chat question. Okay. Well, your talk was very, very clear, I guess. So everyone understands everything. All right. So with that, I'd like to thank everybody and especially Marcus for doing this talk today. And thank everybody for coming and joining us. I don't know if there's any announcements. Adrian did mention some things in the beginning. So I think we're all done. So thank you again. And see you guys in the next one.
Thank you.
All right. Bye-bye.